All right, welcome everyone to the June 30th, 2021 Ockam open source community call. Really exciting call today. I have been excited about this on the calendar for several weeks now, so it's finally here, and I think everyone's going to really enjoy this one. It's a great presentation that we're going to get to from Daniil, who's going to talk about how we've integrated Ockam into Kafka and Confluent Cloud, and how we can do end-to-end encryption and mutual authentication through Kafka and Confluent Cloud. It's really exciting, particularly in this month where everyone is really excited about data in motion. A couple things to kick us off. I just want to remind everyone of our code of conduct. Take that very seriously at Ockam. You can find that on our website. And we apply that to things not only internally, but our external community as well. A great place to connect with us. We run our community on GitHub discussions. You can find that right in the Ockam Network /Ockam repo. Everyone should be on mute as default. If you need to ask a question or something, probably the first and best way to do that is through the chat, and then we can kind of monitor things from there. Again, like usual, this video will be broadcast on YouTube after it's over, so anyone can watch it asynchronously. And the final thing I'll add is that we're always adding to our team, so we'd love for you to check out some of the open positions that we post on our website. Some of them are, let's say, a little bit more opportunistic or active than others. But these are all positions that we will be filling over the next several months or around by the end of the year. So definitely keep in touch with us as we're adding to the team all the time. And with that, I would like to turn things over to Mrinal that will set the stage for and the context for what Daniil's going to talk to us about today.
Thanks, Matt. Hey, everyone. My name is Mrinal Wadhwa, and my goal today is to kind of give you a very quick overview in case you're not familiar with what Ockam is. Ockam is a set of programming libraries and managed infrastructure for end-to-end encrypted, mutually authenticated, granularly authorized communication between devices and cloud services, or devices and other devices. And the goal is to make it easy for developers or application builders to build distributed applications that are secure and private by design. So to enable that, the core of our system is a set of cryptographic protocols. And these cryptographic protocols enable end-to-end encrypted, mutually authenticated secure channels. There are cryptographic protocols that enable entities to have identity profiles where they can keep separate profiles for separate privacy contexts, which can enable you to sort of embrace least privilege and only expose selective information in select privacy contexts. There are cryptographic protocols for establishing keys in a large fleet of devices, rotating them, revoking them, basically key management at scale. There are cryptographic protocols in the system for attribute-based, privacy-centric access control. So essentially, we have this credential scheme which enables selective disclosure. So you can get signatures or attestations on several attributes about you from an credentialed issuer, but then reveal a proof of possession of that credential or signature while only selectively disclosing some of those attributes, which can be very useful in a lot of privacy control type scenarios, or even least privilege in general. And then they're using these sort of low-level building block protocols. We're then building higher-level protocols for things like device enrollment at scale, managing API tokens in a leased way so they can be rotated and revoked if your device is talking to cloud services, and a lot more like that. But at its core, the system is a collection of cryptographic protocols. The one protocol that we will touch on a little bit in detail, at least from a use standpoint today in Daniil's presentation, is secure channels. And at a very high level, secure channels look like this. There is an initiator of the secure channel. There is a responder to the secure channel. The beginning phase is a authenticated key exchange, which involves public key cryptography. So some messages are exchanged between the initiator and the responder. There's some cryptography involved, but the result of that exchange, the handshake or the authenticated key exchange, is a shared secret between the initiator and the responder. And this shared secret is never sent over the wire. It is computed using cryptographic primitives like Diffie-Hellman key exchange. And so once these two parties now have a shared secret, they can then use authenticated encryption with symmetric key cryptography to then start encrypting data for each other. And this is much more efficient than continuing to use public key cryptography. So this is the general idea behind secure channels. You may have come across several secure channel protocols, TLS being the most prominent one. And in code, you can create secure channels by simply calling a function from the Ockam library. So this is what creating a secure channel would look like. But the key thing we've done there is that we've decoupled our secure channel implementation from a specific transport protocol. So something like TLS has fairly tight coupling with TCP. The secure channel implementation in Bluetooth would have tight coupling with Bluetooth, the protocol, and so forth. But in our design, we've decoupled our secure channel implementation from specific transport layer protocols because we have this notion of application layer routing in our system. So as a really quick example, you can say, take this message and send it over hop 1 and then then hop 2, right? You can, in the message, encode routing information of the message. So this message, hello Ockam, can carry with it a onward route and return route. Here I've drawn the message structure in this JSON-like structure, but actually it's tiny binary encoding format. But regardless, it carries information about the onward route of a message and the return route of a message. And so you can get arbitrarily fancy with the routes you want your message to take. You can have 3 hops, 4 hops, 5 hops. Each of these hops can be different transport layer protocols and connections. And these hops can happen in different points in time, which means that you can kind of arrange this flow of messages and encode that in the message itself. So if you combine our secure channel protocol that is decoupled from the transport layer and this routing capability, you can start to describe end-to-end encrypted secure channels in simple function calls. And so in this particular case, I'm creating a secure channel, but my secure channel listener or the responder that I want to talk to is several hops away. And so I can encode the route to that secure channel listener in my secure channel create call. And at the network level, this would look something like this, where the handshake happens, but then to the application is available a channel that is end-to-end encrypted, and the intermediary hops, the hop 1, hop 2, hop 3, see encrypted data and can't actually manipulate or spy on that information. So if you take this basic idea and then you start combining it, you've got this sort of basic building block of end-to-end encrypted secure channels. You start combining that into higher level systems, you get what Daniil's going to show in detail today. But essentially, you can have devices talk to other devices or cloud services through messaging or event streaming systems like Kafka, where there are several transport layer connections involved in the path of the message. But when the message lands and gets stored in Kafka, it is encrypted and cannot be seen or manipulated by someone who has access to that Kafka instance. What that means is that we can have secure and private by design applications that embrace the principle of least privilege. Think devices in your home sharing data and control only with your family's phones, not with some cloud service that kind of pretends you have access, but actually the cloud service and any attacker who can compromise the cloud service also has access. Your car sharing data and control only with you, not with several network intermediaries. Devices in hospitals sharing data only with select doctors and patients, not with lots of service providers that may be operating machines in a hospital setting, or cloud service providers. Devices in factories sharing data and control only with authorized personnel. Microservices granularly choosing which users and which other services see what application data. That's what you could build with this sort of basic primitives in hand. And with this, I will hand over to Daniil to show you how we can do this with Ockam Streams and Kafka.
Thank you, Mrinal. Hi, I'm Daniil Fedotov, and I am going to show what we have in real code running here. So let's start with a bit of an intro. I'm not sure how sharing is going to work over multiple desktops, so hopefully it will. Okay, I'll just share separately. So
Looks
what
good.
are we trying? Okay. So what are we trying to achieve here is end-to-end encrypted messaging using the Ockam secure channels, but we want to run it on top of streaming message brokers like Kafka. And yeah, and space, what? Okay. Yeah. So the problem definition is why we're doing this is we want to achieve message delivery guarantees when we run our secure channels. So we not only want messages to be encrypted, we also want them to be reliably delivered to the ends in our messaging. And since we're dealing with devices and we're dealing with edge devices, they are by definition always run on unreliable networks. And sometimes they even run offline, such as your smart home devices or even your phone. In that type of situation, as practice shows, the best approach for messaging would be stream processing. So stream processing is mostly already solved by a bunch of different providers. There are different brokers like Kafka or Kinesis or Apache Pulsar or others being developed right now. They're trusted, they're reliable, they're already running in enterprise. So that's why we don't want to re-implement that. We just want to use that from our platform. The issue with that is that we might not have a client for, let's say, Kafka to run on some microchip device. We might not have support for the networks that we're trying to provide. Like as Mrinal mentioned, we might want to deliver through multiple hops, which could be TCP, UDP, some radio protocol, and there is no Kafka client for a Bluetooth protocol, at least that I know of. And we also want to allow this end-to-end encryption, and we want to allow all the security features of Ockam to work with that. And the final point is that that's an interesting actually point, is that we want to separate access control from the operations in a way that the service, your cloud service is what you operate, but the users or devices is what have access control. So the operators can change or swap or change credentials or access or even replace clusters if they wish, while the endpoint's actually dealing with credentials. So do not have to provision credentials to your devices or phones when you change something. So in order to actually address this, we are doing, we implemented a small streaming API using the pull model for messaging, which is running on top of Ockam routing protocol. And the integration with the streaming brokers, the message brokers, is happening on the server side, on your either in the cloud service or on your premises on when you run the service. So the operatable part, which is integrated with the rest of the infrastructure, is connected to the actual devices using Ockam routing protocol, and doesn't actually, your device code doesn't actually include any, let's say, Kafka code or knowledge about Kafka. So that's why we're using this API as a simple proxy for streaming operations. The Ockam Stream Protocol, this protocol I mentioned, is described in this link, so you can use this link to read more. But in short, it's providing the functionality to create a stream instance, which is, we can think of it as a Kafka topic, push messages, pull messages, and manage, we call it indexes, Kafka calls it offsets. It called indexes in some other systems, or offsets or something like that, but generally a position of a consumer in the stream. And this is purposely minimal API. It might be expanded in the future, but right now this is enough to get you exactly once delivery and integrate that. You can check more description of the protocol on this link. And we also, on top of this protocol, we implement the client, which okay. We implement the clients which allow your application code to talk through the service instance with the Kafka integration. So this is a simple schema which shows that your app code can talk in through the client through this proxy, put messages in Kafka. This is without any encryption here. We just have plain messages here. And if we, to add encryption, to add secure channels, we just insert secure channel in the forwarding path between your application code and your stream client. And because we use Ockam routing messages the same way that secure channels use Ockam routing messages, we can achieve, we can make sure that messages are encrypted on the way through the system, both to the storage and from the storage, and the arrows here in the middle also should be red. They also encrypted. So all the messages which ever leave your application or enter your application or stored in the storage here are encrypted. And we also provide, because we use Ockam routing protocol to pass our stream commands, stream client API, we can also achieve things like I describe here, is when the stream API itself is sending it requests and responses through a secure channel. And in this case, you don't actually have encrypted messages, but all the communication between your application, your device, or whatever there is, and the service, currently call it hub here, is encrypted. So depends on the boundaries of trust in your system. You can mix and match in this. Right, so the clients are currently, we have Elixir client and we have a Rust client, and Rust client is less feature complete. Elixir client is more feature complete. We are working on the Rust client right now, and to make it in sync, just check the news. We will post stream guides soon. But tomorrow I'm going to show demos using Elixir client. So yeah, you can also find the client implementations on these links. I'm going to use the examples. They are publicly available. I'm going to run the code locally and just run through these examples. So let me share. I guess I'm going to share differently. Okay, sorry for that. So I'm sharing my desktop, and you should be able to see the code, right? Do you see the code?
Yes.
Okay. Good. So to start at the beginning, so I'm going to start with API examples. So we both expose both the API for the streams, and we also provide stream clients as workers you can start in your system, and they do asynchronous communication with the service. But for the start, this is a simple synchronous communication. So in this case, we have a stream protocol create request. We just call that. We have stream protocol push request, and we have stream protocol pull request, which can be used from the code, from the application code directly, but maybe they shouldn't be, because why would you do that? Again, you can implement your own logic and your own clients. It really depends on your typo. So here I'm starting. This is my server console. So I'm starting a server which is currently integrated with Kafka. Just gonna show that we have a stream Kafka index service and stream Kafka service running on this server side, and I'm moving Windows so I have some space. And here is to emulate our device. I'm starting a different console with a client where I'm going to run client commands. So this is a small initialization, ignore that. So for example, when I want to create a stream, which I call my API stream, which will in turn run synchronous command through that, through our stream API. And this will call the server. There's some logs you can see here. And what it returns is actually a route you can use in your application to get to the stream instance. This is currently random streams. And what else you can see is that, hopefully it doesn't lock me out. No, it doesn't. Okay, this is a Confluent Cloud UI where we just got my API stream topic created. So each stream that we create using the stream API is creating a topic in Kafka. And so let's say if we want to publish some messages, again, this is just a convenient way to call this, to call the stream API. And let's say we publish hi 1, hi 2, and hi 3. So it returns a message on a certain index. This request ID is the same because that's the client, the client which defines that. So ignore that for now, that it's one. In your client implementation, it should be different. But we can see that there are 3 messages there, index 0, index 1, and index 2. And if we check the stream in the Kafka UI, we have the high 1, high 2, high 3. That maps the Kafka implementation maps it mostly one-to-one. So a stream is a topic, and indexes are offsets in the topic. And then the pull API is also pretty simple. So here we pull in from offset 0 and we pull in 1 message, and that's what we get. The same way from offset 1, if we want to pull 10 messages, we get all the messages we have. Currently, we have only 2 here. So that's the basic API, stream API. The application can use that. The application can implement their custom clients with custom characteristics, and also application can pull messages when it wants, and using the index while it can store it somewhere to retrieve messages that were in queued before. So there's no limitation here. That is also a simple index API. I'm just going to show that it integrates with the Kafka offset storage. So here we don't have an index for this consumer. And if we go into save index for this consumer, we get it. So these are the built-in blocks on which we are building streaming clients. And now to get to a bit more interesting scenario is this example. It's all in the repo, so you can try it yourself. But this example is running a streaming client. There's some setup configuration going on here. But the idea is that the streaming client will start a consumer, which we provide in Ockam library, start a publisher, and those would be running and either forwarding messages to the stream or constantly consuming messages and running the message handler callback on all messages they get. Currently, message handler callback just forwards message to the next worker in there. And this next worker is called receiver. So receiver will log messages, and that's what we expect. So when we send message to a stream, we will expect a receiver to log it because it was forwarded by the consumer. So let's run that. I'm just going to quickly reset this console so it doesn't have any history in there. So this example will start publisher consumer and run a single message throughout. So that's what we should see. It's initialization, and here we go, received message, I am a message. Also, we use my client stream as a different stream from the one that we used in the previous example. And if we look at the topics, we see my client stream was created, and we can check messages in there in Kafka. So it's all straightforward for now. So here's I'm a message, and we can send more messages through the same stream. I can send 100 messages. Now we should receive them. And here you go. We have 100 messages in there. Something keeps stealing my focus. So, okay. Here you can have message number 86 and up to 100. So it's all straightforward. It's just proxies requests to Kafka API. Nothing fancy here. And now we get straight to the fancy part, is this how we call it, sample stream bidirectional secure channel. So what it does, what it's trying to achieve is ping pong between 2 nodes through secure channel through streams. So we currently seen that a stream can deliver messages, and we know that secure channel is encrypting messages and also forwards them. So this is a ping pong, two workers which exchange messages. So if we quickly run just simple ping pong on a node, we'll see what we see without streams and simple ping pong. This is what we see without streams and secure channels, right? So the number is just increasing. We see ping, we see pong. So now if we do run secure channels and streams, so what's happening behind the scenes is that on the Pong node, we create a Pong worker, which will reply. We create a secure channel listener, which will create new secure channels and create secure channel responders. And we subscribe, which will create a consumer and configure this consumer to forward messages in the way that the worker which receives them can reply to them using Ockam routing. And for the other node, we also going to create, in this case, ping worker. We're going to subscribe to the ping topic, ping stream, and we're going to create publisher with the knowledge of both Pong stream and ping stream in order to be able to tell the Pong worker on which stream it needs to reply. So in this case, we have two streams, and one node listens to one stream and another node listens to another stream, and they can reply to each other. On top of that, on top of this publisher, which knows how to publish messages and tells the stream where to reply to, we run a secure channel, which will do our encryption. So let's start this. I'm going to start Pong on one node. I'm quickly going to start another node. And on this node, we can see that it's initialized, it's starting consuming from 0. And we can also check that in the topics, we have the Pong stream. Yes, we have the Pong stream because we didn't run the second one. Yeah. So here on the second node, we just do run, and this will start a second stream, and this will start actually communication because, yeah, here it goes. So it's received Pong for 0, received Pong for 1. So there is a message going back and forth with increasing number, and we can see the messages here. If we check the actual ping and Pong messages that we get, you can see there, so some gibberish going on here. They are encrypted by secure channel. So even if you know what's the schema here, you still won't be able to decode and know what's going on in those topics. And this communication keeps going. Here the Pong replies. What our stream integration is providing on top of just secure channels in this case is that, for example, if we have network interruptions, and to simulate that, I'm just going to stop the server right now. So the server is stopped right now. There's no server. So basically, both applications lost connection to the service. It might be one of them which does that in real life, most likely, but it's just easier to reproduce this way. And here you can see that there are some request timeouts going on. The stream consumer is not happy. Now, as we know, they are timing out. We can we start our service. Let's say service comes back up, and what's going to happen is consumers, if you see consumer here restarted, it actually received some message which was in the stream while when consumer was down. So this message being point 424 was stored in Kafka essentially while the whole system was down, and then it recovers and continues to do ping ponging. So this all was running through mutually authenticated secure channel. This all was running through Kafka as a message storage, and devices can be disconnected or reconnected. And that's pretty much it for the demo. I'm going to enter play just so it doesn't do anything. So what do we achieve through that? So we have reliable message delivery. We have buffer in the Kafka. We have at least once delivery. Haven't seen in this demo, but in some other demos, we've seen some message duplication, which is a sign of at least once delivery. We can have network interruptions. Ockam routing allows us to do network agnostic, protocol agnostic message delivery, and we achieve end-to-end encryption using secure channels. If you want to try the examples yourself, there's an additional thing you can do in this secure channel example, is that change TCP here and here, and this places to UDP, and it will run through UDP, and it doesn't need to be TCP. It can be something else in the future, some other protocols. So that's it. Thank you.
Thanks, Daniil. So, to very quickly conclude, essentially what we saw is the ability to create end-to-end encrypted secure channels that can go through multiple network layer hops. So you could have your first hop is Bluetooth, your second hop is TCP, then the message lands in Kafka, is now stored in Kafka, and then some other device can, over a TCP connection, consume this message, yet the message remains end-to-end encrypted. And this production of the message or creation of the message and consumption of the message can happen in different points in time. So the publisher can publish now, the consumer could consume tomorrow, and it would still be an end-to-end encrypted message. So we're able to do this kind of arrangement of secure communication that is safe against message tampering, safe against eavesdropping of messages, and also safe against forgery of messages, because both parties here are authenticated and authorized as we build our authorization layer into Ockam. So thanks, Daniil. That was an exciting demo. What you saw today was kind of the internal examples as we play play around with this and build, put the things together. In a few weeks, towards the end of this month, we're planning to have the Rust implementation of streams in a decent shape, and then we want to have some end user guides with simple functions that you can call to call all of this, so you wouldn't have to write hundreds of lines of code. It'll be 2 or 3 lines of code to get end-to-end encrypted streams passing through Kafka, maybe in Confluent Cloud, maybe somewhere else. And then over time, we will also develop add-ons that are not Kafka, but some other messaging message broker. So watch this space and keep an eye out for our Kafka add-on for Hub, which we will talk about in more detail and have some guides on towards the end of this month. And we'll have some examples of using end-to-end encrypted channels with Kafka in Rust coming out in a few weeks as well. Thank you, everyone. Thanks a lot for joining.